This video we're going to talk about titrimetric analysis. So different from measuring physical properties, titrimetric analysis actually is a chemical method because in the reaction which will be include the reaction between the acid and alkaline like a neutralization. So for following the progress of reactions, actually we are measuring the change in concentration of one of the reactants or product, and the method that we use is called titrimetric analysis. Remember, okay, one more time, this is a chemical method. So what is titrimetric analysis? Actually we are using titration to determine the concentration of reactant or product at regular time interval. So you just imagine if one of the reactants is an acid like this, and then they will give up product. If acid is one of the reactant, as time goes by the concentration has to be going down. So if it is a concentration time graph, we'll have something like this. So by measure the slope of this graph, we can measure the rate. But if we have this time not a reactant, okay, is an acid or alkaline, the product, okay, if it is an NaOH, for example, like this way, then we will know that the concentration of NaOH as time goes by, it should be increasing because it is one of the product. So if we measure the concentration of NaOH against time, then we will have a product time graph like this. Okay, so by measuring the slope of the tangents of a particular point, we can measure the rate of the reaction. So basically, when can we use it? When one of the reactants or product, okay, is acid or alkaline, then we can use this titrimetric analysis to help. But in future, okay, if you learn something called redox titrations, so at that time actually you can also use titrimetric analysis to measure the concentration of the reducing agent or oxidizing agent. So not only acid and alkaline, but also sometimes OA or RA, we can also use this method to measure the changes in it. So basically, there are 3 steps for titrimetric analysis. So you have like withdrawal. We're going to withdraw a small portion of reaction mixture with pipette at regular time interval. So for example, this is the reaction mixture. As time goes by, okay, we'll have like using a pipette and then withdraw one portion, say for example 10 cm cube, and put it in a conical flask. Well, after a while I will take another 10 cm cube, okay, in a conical flask, another time another 10 cm cube in a conical flask. Once we take it out, okay, actually we'll do another steps which is called quenching. Quenching means stop the reactions. So for example, after I take it out, okay, I will then put it into a ice water bath, or I may pour some cold water in it, okay, to stop the reactions. Okay, we try to lower the temperature, okay, or lower the concentrations of the reactants. Both of that, okay, it can lower the rate of the reactions and also keep the concentration of the reactants unchanged. So first we're going to withdraw it, okay, and then we'll quench the reaction. Finally, okay, we're going to measure the concentration of it by doing titration. So withdraw, quench, and titrate are the 3 steps for titrimetric analysis. So what is quenching? Just as I mentioned, quenching means stop the reactions. This can prevent further change in concentrations of the chemicals. Okay, if we have like concentration of the HCl, if we don't quench it, we just withdraw it out from a beaker, okay, and then we put it in a conical flask. The reaction inside, it may still keep on going. Okay, so this is not something that we want, so therefore we have to quench it. Okay, so how to quench it? We can cool the reaction mixture. Okay, this is by lowering the temperature. So if we have the reactions, okay, I put it in ice water bath. Okay, lower temperature, it can reduce the rate of the reaction. So this is method 1. Method 2, by diluting the reaction mixture with cold water. So we can, like this is the reaction mixture, I can pour some cold ice water in it. Okay, so when we have cold water add into it, okay, there are 2 effects. One will be lower the concentration of reactant because you are diluted. At the same time, because the temperature is very low, so therefore it can also reduce the rate of the reactions. Third, okay, we can also remove the catalyst. Okay, this one is not included in the textbook, but some of the reactants, okay, or some of the reactions, they may have a solid catalyst. When they have solid catalyst, okay, actually you can just simply filter them off to stop the reaction. So these are called quenching of the reactions. Okay, our purpose is to prevent further change in concentrations of the chemicals. So after we quench, okay, then we will start the titrimetric analysis. So we'll just give an examples here. This is called alkaline hydrolysis of ethyl ethanoate. Ethyl ethanoate, later on you'll learn that this is called ester. Alkaline hydrolysis, this is the media, which is alkaline. Hydrolysis means break down with water. So we are having water to break down the ester. Okay, so this one, okay, is the ester, ethyl ethanoate, and then it is an alkaline media, so I put NaOH. Throughout the whole equation, you will find that, okay, this one is the alkaline, is the only alkaline. Even this one have an OH because this is a ethanol. It actually is not an alkaline, okay, so don't mix it up. This one is not an alkaline, okay, I have to write down, not alkaline. Okay, later on you'll learn this one. Actually, this one's called ethanol. Okay, it's a kind of alcohol. Okay, so throughout the equation you'll find that we got one alkaline, and this is at the reactant side. So we'll expect the NaOH as time goes by, the concentration of it will going down. So basically we'll allow the reactions to start. We have NaOH here, we have the ester here, ethyl ethanoate. We mix it, the reaction start. Okay, and then as time goes by, a small portion withdraw. So small portion withdraw. How long? Okay, we'll withdraw one every 2 minutes. Okay, so first we'll withdraw. After we withdraw, immediately we quench it. You see that this time we have add ice, distilled water in it. Okay, so therefore we'll lower the temperature and also dilute the reactants. Okay, and after that, okay, we will put this one into a titration. So basically withdraw, quench, and then titrate. Okay, withdraw, quench, and then titrate. So the process, okay, we'll have the reaction start, mixing it to start, regular time interval, withdraw with pipette. This one very important. Quench the reaction by pouring them into ice cold water. So we stop the reaction, prevent the change in concentration. Finally, we titrate against standard hydrochloric acid. So this is normally the process how it carry out, okay, the process of titrimetric analysis. But we do have some disadvantage of it, okay. We have disadvantage of it because in the process, actually, you keep disturbing the original reaction mixture. You try to take out small portion out from it. So the original reaction mixture is disturbed all the time, okay. So this may have an effect on the reaction rate. Other than that, okay, because of the fastest way that you can withdraw the small portion out, maybe 1 or 2 minutes, okay, you can't monitor the rate, okay, like measuring the volume of the gas produced or the pressure change in the reaction system that continuous, okay. So this is a discontinuous monitoring, okay. So we'll say that, okay, the continuous monitoring of the reaction mixture is impossible, okay, of the progress is impossible. Okay, so these are the two disadvantages of titrimetric analysis. So let's have a look of the examples. Okay, so right here, okay, we have alkaline hydrolysis, ethyl ethanoate. Okay, so the sodium hydroxide we have used is 100 cm cube, okay, and 0.02 m NaOH, and this one will mix with ethyl ethanoate every 2 minutes. Okay, so now we're going to highlight. So this is the reactions every 2 minutes. Okay, we'll have withdraw, and then we pour into ice. So normally this is the second step. We know that this is a quenching steps. Okay, so this is quenching steps. So withdraw, quench, okay, and then the last part will be titrate. Titrate with acid. Okay, so basically you have 3 steps: 1 withdraw, 2 quench, 3 titrate. Okay, because normally this kind of question is a little bit long. Okay, the question is like a paragraph. Okay, you have to focus. The real titration reaction will happen at the last. So therefore, this NaOH react with the HCl is the titration reactions. Okay, but the one before, like NaOH and ethyl ethanoate, that one, okay, is just the reactions that we are monitoring at. This one is a titration reaction. So basically, for a titrimetric analysis, there must have 2 reactions involved. Okay, one is the reactions, one will be the titrations. Get it? So you got some data here. Okay, we know that the HCl we use to titrate, okay, we're getting less and less and less and less, because okay, we know that the NaOH concentration will decrease with time, as NaOH is a reactant. Is that right? This is a reactant. So therefore, as time goes by, less amount of NaOH will present in the withdrawal solutions. Okay, so name the apparatus, withdraw 10 cm cube. Remember, okay, it is a pipette, but not good enough. You have to measure 10 cm cube. So it should be 10 cm cube pipette. Okay, easy for this. Second one, why will a small portion pour into ice cold distilled water? So this is a quenching step. So just tell them quench the reaction and also prevent further change in concentration of NaOH. I prefer to answer both of them. Okay, so that will be very clear. Okay, what means by quenching and what concentration you want to remain the same. Okay, and then part C will be the calculations. Calculate the concentration of NaOH at 4 minutes. 4 minutes, that means this one. So basically, you just use this one. 4 minutes. Okay, 5.5 cm cube, and then 0.1 m. Okay, we use that to find out the number of mole first, and then mole ratio will be divided by 1 times 1, find the number of mole of NaOH. And because it is in a 10 cm cube portion, okay, after we got the number of mole of NaOH, we divide it by 0.01. This is the volume, okay, of the reaction mixtures. Okay, so this is the concentration. Got it? So MV, find out this one, mole ratio, find out this one, divided by volume. Okay, so you have 0.05 mole per dm cube. Okay, I prefer all the time have the mole per dm cube. Okay, especially in the rate concepts, rate chapters. So we try to convert all the volumes, okay, into a concentration for NaOH, and you got a table like this. Try it out a bit, okay, by yourselves. Next, okay, we're going to plot a graph of concentration of NaOH against time. So basically, concentration of NaOH against time. Time have to be minutes. Concentration have to be mole per dm cube. Okay, as time goes by, the concentration will drop like this way. Okay, so and also we have to find out two disadvantage. Let's have a look. So the concentration time graph like this. Okay, remember the unit. Okay, and then it will be at the beginning, the initial rate is fast. Okay, and then we get slower and slower. Finally, if the reaction stop, okay, it will go horizontal. Okay, the two disadvantages mentioned just now: original reaction mixture will get disturbed whenever we withdraw a small portion. At the same time, continuous monitoring of progress is impossible because the fastest that you do is just 2 minutes. Okay, so in the middle, actually something happens. Okay, but you can't measure. So one more examples, okay, it will be class practice 36.8. I just want you to feel the process must be withdraw, quench, and then titrate. Okay, so we look for these three words here. So when at regular time intervals, okay, we'll have like 10 cm cube portion of reaction mixture was withdrawn. Good. Okay, first word, withdraw, and then pour into ice distilled water. So this one is quenching. Okay, quenching. Maybe they won't show you the word of quenching, but you know that after follow up with the withdrawal must be quench. Okay, and then the third part, okay, it will be a titration, but this titration this time is sodium thiosulfate. Okay, maybe you don't know what is the reaction between these two. No worry. Okay, this titration is just like what I've said. This is a redox titration, because you can see the ON, it will change from 0 to -1. Okay, so this is a redox titrations. So basically it will be the same. Okay, because they tell you that this is a molarity, this is the volume for the sodium thiosulfate. So this will be 6.5 cm cube, and then 5 times 10 to -3 mole. So basically this one is per dm cube. MV, okay, you got number of mole of this one, okay, and then okay, divided by 2 times 1, then you can find out the number of mole of I2, and afterward you divide it by the volume and you can find the concentration of iodine. So this is the steps. Okay, you just do this on your own. Remember, purpose of pouring reaction mixture into ice cold distilled water. This 20 cm cube is meaningless. Okay, remember the most important is quench the reaction. Quench means stop. stop what things, stop the reactions, okay, and also prevent the changes in concentrations of the iodine in this case. So summary, okay, so follow directions. Actually, we are trying to measure the change in concentration of one of them, okay, by the method called titrimetric analysis. Remember, this is a chemical method. If we have one reactant or one product is acyl alkaline, we can use this method, okay. But just now you see that, okay, if one of the product is OA or RA, you may also use this one as well, okay, because we have redox titration. So the step basically withdraw, quench, and titrate. You must see these two words, okay, but quench may be a little bit subtle, okay. Quenching method, okay, we can cool with ice water, we can dilute with ice water, we can remove the catalyst, okay, by doing like filtration. All these can stop the reactions so that we can prevent the concentration of the reactant changes, okay. And then number 6, okay, graph. Okay, so we have concentration time graph. And the disadvantage, okay, we'll try not to we don't want it to disturb the original reaction mixture, and also we want to have a continuous monitoring of progress. However, this seems impossible because the fastest you can do is just 2 minutes. Okay, so that's all for this video. Bye bye.